diagram. Whereas bond graph is an acausal model. So you draw it from physical principles. After that, you put causality and equations are automatically derived. So equations are derived from this. Whereas block diagram, if you already have equations or if you already have a causal model, then you can construct a block diagram. Alright? So it's not very easy to change a block diagram. If the model changes or small change in model, PC may change a little, whereas PD may undergo significant change. Because the structure of equations can change. In bond graph, you are not really deriving equations. If you have a software, it will derive the equation for you. Whereas this block diagram, if the equation format changes, then the entire model will change. So that is the basic difference. So you cannot say that I will take a system and draw its block diagram directly. You have to first derive its equation, then draw its block diagram. Or first draw it some kind of model like a busy model or causal graph model or different kinds of models. And from that model, you can translate it to a block diagram. You cannot directly draw a block diagram unless you have equations. So I will draw the simplest block diagram possible.
Sir?
Yes.
So while deriving the block diagram, we don't know what the diagram, like the system, looks like. We only know the governing equations, and then we have to derive the diagram.
Yes, I will show. You. Okay. I am going to show you. Okay. So let's say we have spring mass damper system. And some FT, let's say. So you can directly write down its equation. Next double dot. X is equal to FT. That's our governing equation. So this block diagram will have exactly same states as we have in our bond graph. We will rewrite this equation like this. We will write X double dot equal to 1 by M. So this is the highest order term. Rest things we take two other sides. Ft minus Rx dot minus Kx. So that is the first thing you do. So we do Ft minus Rx dot minus Kx. Now how to represent all these terms? This Rx dot, let's say. This is represented as, to take, this is a signal. Block diagram is a signal. R3 is a gain. So we put R as a gain. Similarly, Kx will put as a gain. How to do this sum? This ft minus rx dot minus kx, you will put a sum block. Something plus, here minus, minus. Let's say this side rx dot comes, this side kx comes. So kx is minus, rx dot is minus. And this side ft comes. The result is ft minus rx dot minus kx. So this, and after that, I will put again 1 by m, this part, this 1 by m part, and this is x double dot. So that is one representation. This is called sum block. Everything is a block. Game is a block. Or you can also draw it in Simulink. There are different methods. You can draw a rectangle like this. Right? Let's say plus, minus, minus. This also is possible. But there will be no plus minus here. In the output one, there will be no plus minus. Only on input signals, there will be plus minus. The input signals, whatever they are. ft, x, rx. Okay? So that's how you can draw. So let's represent that equation then, full block diagram. Very simple, very, very simple. This is ft, which we put as a source. Let me put it like this. This is ft, source, is a source. Then we have to plus, let's say put minus here, minus here. You have to, according to that equation, as many plus minus you have to order. Then here we have that entire term. We divide by 1 by m. This becomes x double dot. Okay? So rest of the things will come here. Somewhere here, it will come. Now this x double dot, we will put a block integration. So what does it give? It gives me x dot. Okay? So one integration, I get x dot. So here I can give initial condition. To every integration block, I can give initial conditions. Now this x dot has come. I do another integration. I get x. This x, now I take this out, multiply, again k, goes here, this goes here, this kx. Likewise, from somewhere, you can draw from anywhere. So this is from here, I take r, this r x dot. So this is my complete block diagram. If you want to plot something, if you want to plot, you put a sync. is sink. Plot. So you are connecting your sink here, you plot X. If you connect a sink here, you get X dot. So whatever you want to plot, you put sinks. So inside sinks, whatever results come, those results will come. This is sink. So sinks do not affect rest of the things. Right. Your main system, right, is composed of a forward line, and these lines are called, these are feedback lines. This is also a feedback line. And this is our forward line. So is it clear, this picture? Is the picture clear?
Sir,
Yes.
sir, the line from the integrator to K,
Integrator to K. Yes, second integrator to K. Yes.
second integrator to K, how did we say that it was a feedback line? Like the K could have been drawn in front of the integrator, then we wouldn't be able to recognize it as a feedback line,
Then
right?
it will not be a feedback line. Then it will not be a feedback line. Feedback line is one, okay, which comes back to the subjunction. Okay.
So the direction of which is simply reverse.
Yes, yes. Okay.
So this model and that model wouldn't be the same. Like if the K is drawn in front of.
They will not be same. K may appear in forward part.
Yes, sir.
In this case, it's appearing in the back, the feedback part.
So how do we decide when to draw it forward and when to draw it reverse?
From the equations. Okay. From the equations, or I will show from our bond graph. How do we get this? Okay.
Yes, sir.
We will draw it from bond graphs without writing equations.
Yes, sir.
Okay. So this is the model. Right. So whatever you want to plot, just connect a sink. You can connect it anywhere. And the source can be various kinds. In MATLAB, you will get sine, cos, all kinds of things, step, ramp, all kinds of sources are there. So now let's try to draw this. Okay. You see this block diagram model, and instead of this, let's say this spring damper is there. Below the spring, that damper is there. Right. If the damper is below the spring, this equation will undergo large changes. Right. It's a big change. Whereas in bond graph, it will be simply one junction becomes zero junction, not a big difference. All right. So let's see how we draw it from bond graph. Easy. Transformation. Same system. 1, I, So what we will do is, for each junction, what we have? 1 peak relation, that is derived from, for this one, sigma EI is equal to 0 or sigma FI is equal to 0. For a one junction, sum of efforts 0, for 0 junction, sum of flow 0. And many strong relations. So for example, for this one, let's say bond numbers 1, 2, 3, 4. So we will have, let's say, F1 is equal to F3 is equal to F4 is equal to F2. So F1 is equal to F2, F3 is equal to F2, F4 is equal to F2. So this weak relation, this is a sum block. And this one is a distribution. Node. Right? So one sum block, and there will be n minus 1 distribution nodes. So from one distribution node, you can take out n minus 1 branches. That's it. So what do we do? What is our sum block for this one? For one junction? For this one, we have first we give causality.
Sir, this each junction can be 0, 1, anything.
Yes, junction can be anything. Okay. And so for each junction, we will get a sum block. For one junction, we will get a sum of efforts. For a zero junction, we will get a sum of flow. So like we write our equations, but we will not completely derive it. We will only write it in parts here. So we have our source of effort. Causality doesn't change. This once we give there, rest of the things come causality here. So what we have our relations for this junction only. We have E2 is equal to E1 minus E3 minus E4, and we have F1 is equal to F2, F3 is equal to F2, F4 is equal to F2. These four relations we have. So I will draw this. As for this relation, first I am writing weak. I may have to write weak relation first, may have to write the strong relation first. I don't know. So I am writing here a sum. This is the E1. From somewhere E3 comes. From somewhere E4 comes. It will come from somewhere. This is plus. You can put plus outside or inside. Doesn't matter. Okay? For representation purpose, it can be outside or inside. In Simulink, it will be inside. The result is B2. That's it. Okay, so one sum block I have written. Then where is this E2 going? This is the output. E2 is going here. E2 is going to I element and becoming F2. This is becoming F2. So we will do that. So E2 becomes F2. How does E2 become F2? 1 by M integration or integration 1 by M. Doesn't matter. You can do. E2 is F2. F2 equal to 1 by 2 is 1 by M integral to dt. So that's what we did do. So what we get now? F2. Okay? Very simple the way we write equations, but we are not going to reduce them. Now we got F2. Now this F2, what we will do, we will put a distributor. So F2 here. This is my distributor. It's nothing, it's just a joint. This 3, 2, dot. So some distributor, let this be F2 is equal to F3, let it be F4, and let something be F1. Okay? So F2 is branched. has to 3 outputs. Now where does this F1 go? This F1 goes to source. This F1, this is going to source. F1 is going here. And the effort is independent of this E1 is independent of F1. So this is useless. Goes to source. So we will remove that. F1 is gone. So anything that goes back to source is junk. Right. So we remove that. Now we have 2 more elements left. What are they? C and R. So we will represent the C and R relations. That's it. So what relations we have for C and R? So for C, for the C element, we have E3 as per causality is equal to K times integral F3 dt, that is KQ3. Okay. And for R element, we have E4 as per causality is R times F4. That's it. So F4 we have, take it, multiply with R, get E4 and F3. You either integrate first or multiply with K first, doesn't matter. Integrate, then multiply with K. This is Q3. This, our block diagram is complete. You can connect sinks wherever you want. Sinks are separate things and you put your source. Whatever it is, source S1. So is that clear? This picture? So we are just representing whatever strong and weak loss of the junctions in terms of picture, and whatever are constituent relations of elements. At the beginning of writing equations, we write the equations for each element as per causality. We do that same thing here in terms of a picture. But we do not formally then reduce this to a state space form. It's not required. For our simulation, this is enough. So is this part clear or not?
Sir,
Yes.
the what do you say? A signal between 1 by m and the first integrator,
Ah,
could that have been drawn in the reverse direction and this everything followed in
yes,
the
yes, see. Okay, if I draw like this, okay, then initial conditions to this will be x dot at t is equal to 0. Okay,
okay.
and
Yes.
x at 0. If I draw it reverse, then this will be momentum at t is equal to 0. Okay. So if I first put this integration, then E2 integration will become momentum. So I should give momentum at t is equal to 0 and then followed by 1 by m. So that's not difference. Okay, no difference here.
So like
Alright?
between forward links and backward links, there's not much difference.
Nothing, not much. Not much. Okay? As long as
Ah,
mass and other things are constant, it doesn't matter.
yes, sir.
Okay. So let me draw a slightly different one. Take some like this. Let's modify that. I'm just changing a little to show how the block diagram has changed. Instead of that series, I have put parallel. Yes. Our bond graph parallel doesn't change much. What we have, source of effort, 1 I is to m. Then you have 0 instead of C and R appearing at one junction, we have 0 CR. So small sense. The causality. Yes. Yes. Here. Then we see strong bond comes here. So that's it. Okay. Give some number. One, 4, 5. Okay. So now we have two junctions. We have two junctions means two sum blocks will appear. Two junctions are there. At one junction, sum block will be sum of efforts is equal to 0. At 0 junction, sum of flows is equal to 0. Alright. So that has to be done carefully. At one junction, sum of efforts. At 0 junction, sum of flows. And the distributions and other things we will do. So let me start with one junction. Actually, you can start with anything. And that block diagram, you will have a lot of crisscrossing. With experience, you will know how to where to start and how to organize that block diagram so that there is not overlap, not much of overlap. So that is the experience part. That there is no rule to tell you how to draw a block diagram which will not have overlaps. So I start with a sum junction. So we have E1 from somewhere. This E3 will come. I don't know. Okay, I put it from top. This is a plus. E3 is minus. It will come from somewhere. We get E2. Let's go by what students are saying. Let's first integrate. Then 1 by F. Get F. So that's straightforward. One junction and I element are dot. So E1 minus E3 is E2. E2 is integrated divided by mass is F. So we have F. Now F2 will be divided into two parts. F2 one part will go to, one part goes to F1, which is useless. F1 is source. So this part is actually not there. This is not there. So we will not at all draw it. Now this F2 goes to F1, F2 goes to F3. So we have F3. So F2 becomes F3. What color I have? This is F3. Okay. Now we will go to the next 0 junction. First one junction is complete. So 0 junction. At F3, what we have? At that 0 junction, strong bond is 4. So F3, another sum. You can put inside this sum a thing like this if required. So at that, output is F4. F4 is F3 minus F5. So F3 is plus, F5 is minus, output is F4. So we have got this F4. Now what to do? F4 is integrated. This becomes Q4. Here, of course, this is E2. So we have Q4. Q4 we multiply. Stiffness K. We get E4. So we got E4. Now this E4 E4, this is weak relation at strong relation at zero junction says efforts are same. So E3 is E4, E5 is E4. So I will take one part E3, another part E5. So E4 is E3 and E4 are same, distributed from here. Alright, this is distributed. Now this E5 is going to R5. Look at this causality. What is there? R like this. Effort is going like this. Flow is going like this. Here F is equal to E by R. Okay? So effort is input. 1 by R. That becomes flow 5. And this, so that part is complete. Everything will be completed. Nothing will be floating. This E3 is floating out here. Right. I will make a small change here. In my picture, I will erase that E3. I will put it in bottom because it's coming from bottom. Right. I could have taken it from here right side and got it on top side. So it's not a problem. I am putting it at the bottom side. So I will put it at bottom. What was it? E3. Minus. And this is what is directly coming from there. Okay. So this is how it came. Here is of course source. So I can redraw this model in a little simplified way. Looks more complex. So maybe I will draw it. Look how it was. It is source of effort. 1 M. Then we went to state K. Sum plus minus. K. By R. Okay. So this is our model. So this model and that other model are completely different. That block diagram, even that block diagram, you cannot easily modify it back to this one. You have to put another sum and some feedback. Now, if you look at this, there are two forward paths. This is a forward path, big one. This is one feedback. This is another feedback. Two feedback paths. Okay? These things are also called loops. This is loop. This is also a loop. You see, you go like this, go back to that same sum. Likewise, start from here, go forward, that is a big loop. Okay, so there are two loops. We'll come back to these loops later on. So how this picture is drawn, is that clear? Is the process clear how the picture is drawn?
Yes, sir.
Okay. So usually you will draw exactly this kind of a picture in MATLAB. In some places, you may find this integration block is given as one by S. Instead of integration, you might see it is given as 1 by S. If you remember Laplace transform, Laplace transform, Laplace transform of function, let's say ft is, let's say, fs. Then Laplace transform of integral ft dt is given as fs by s, or 1 by s times fs. That's why this integration in Laplace domain might be given as 1 by s. So if you are going to some version of Simulink and you say there is no integration block there, it's actually given as 1 by s block. So it might appear as integration block or it might appear as 1 by s block, all they are same. Alright? So I will take up slightly complex one, slightly, not very deep. Let's say motor plus motor shaft is, let's say, rigid. This has JD. This JD is disc plus rotor of the motor combined. Then you have radius R and some rope hanging, let's say. Simpler one, let's take this. You can put MG, no problem. Is there? So let's say this is resistance R, this is supply voltage E, this has mu motor. So I have taken specifically this example because this example contains your AC, ICR, EF, EY. Except source of flow, everything else is there. So I can show you how whole thing is done. So I will draw its model. So I will draw its model a little bit sideways so that my block diagram, I need to have space. This block diagram is not going to be very small. Block diagram is not as compact as a bond graph, so I will need some space. So I am drawing it here. I don't know if I will be able to complete block diagram in this place. So let me draw a C, very small one R, then we have GY, UN. Never put an arrow over GY. GY doesn't have an arrow. Then one I, that is JB. Then you have transformer, that is R. Then you have zero junction, E is to K. Then you have one junction, I is to M, AC is to minus MC. Okay. So this is our model. We will put causalities in this model. Source of effort, Then this I, oh, this SC was there. Okay. So this I, then these two will come here. Then this generator will come here. This R will come here. This transformer will extend here. Then we give this I. So this comes here. So this comes here. So this is our Gaussian model. Once a bond graph is Gaussian, it is equivalent to a block diagram. A Gaussian bond graph, before causality, it's a bond graph, proper bond graph. Okay. Without any computational structure. Once you put causality, you have computational structure. And then only you can convert it to a block diagram. So, put some bond numbers. 1, 2, 3, 5, 7, 8, 9, 10. Okay. So let me draw the block diagram. How many junctions we are having? 1, 2, 1 junction, 3 1 junctions, 1 0 junction. So we are going to have 4 sum blocks. 4. Not a small amount, 4 sum blocks. So I will conserve my space. I will try to draw my E1 here. Small scale. E1. Sum. From some side I will bring E3. I am not drawing it. E3 will come here. I don't know whether it will come at top or bottom, so I am leaving it. I will check which way I can bring it. The result will be E2. This E2, as per causality, it will be divided by 1 by R. 1 by R. That is the resistance of the armature coil. Then this becomes F2. F2 will be divided to F1. So that's terminated. So I am not putting this. So F2 becomes F3. It's also F3. F2 is F3. So now this F3. Now, I have to bring here E3. Remember, I have to bring here E3 from somewhere. I will put this E3 here. The minus sign. This is plus. So F3. Now, once for this gyrator in this causality, what relation we know for this gyrator? E4 is F3 times mu n. So I will put F3 multiply with mu n. I will get E4. So I am not writing two relations simultaneously. I will write the second relation afterwards. Right now I am writing F3 into mu n is E4 as per causality. I will get another relation F4 into mu n is E3. That will come. After I find F4, I will write that relation. So this will be E3. E3 is again mu n. But this side should be F4. I will get F4 from somewhere. I don't have that right now. Now this E4 goes. Then this one junction with bond numbers 4, 5 and 6. We have a sum junction. So we put sum of efforts is equal to imbalance. E4 minus E6 is E5. E4 minus E6, let's put here E6 plus minus E4 minus E6 is E5. Now once we have E5, inertia we know. Integral causality inertia, E5 is integrated, becomes P5 multiplied with 1 by mass. 1 by mass here is JB. we get F5. So up to this, is it clear? We have got F5. Students, is it clear up to this?
Yes, sir.
Yes,
What
sir.
you are saying?
Yes,
Other?
yes, sir.
Okay. So we got F5. Now F5 will be distributed. F5, F4 is F5, F6 is F5. So F5 becomes F4. Is this F4, and it also is F6. So 2 parts it is distributed. Now this F6 we have transformer. So as per causality we have F7 is equal to R times F6. So we do that. F7 is equal to R times F6. Multiply with R. We get F7. And we will get E6 is R times E7. We will write that afterwards. So F7 comes. Once F7 comes, this zero junction. At this zero junction, what we have? Sum of flows is equal to 0. F8 is equal to F7 minus F9. So F8 we'll find from somewhere F8. So F7 minus F9. Somewhere F9 I will bring. Yeah, I have F7. Let's put from bottom F9. Plus, this is minus. The result is F8. F8 goes to string K. So we will integrate. Then multiply with thickness K. We get E8. So it's straightforward. We got E8. Okay. So this is gone for zero junction. Once we have got E8, E8 is distributed to again 3 parts. What is it? E8 is E7, E8 is E9. So E8 I distribute it to E7, I distribute it to E9. Once we have E7, we know this relation. R. This transformer, for the transformer, we had 2 relations. F7 is equal to R times F6 and E6 is equal to R times E7. So this we are done first, this comes second. So whenever this appears, we put it. So once we have got E7, we distributed it into 2 parts. We got E7 and E9. Now we have this last one junction, 9, 10, 11. We have 9, 10, 11. So last one junction, again another sum block. Here E10 is E9 plus E11 is E11 plus. This is plus, this also is plus. Result now is E10. E10, of course, we integrate. Its inertia element becomes P10. We again multiply it with 1 by n. We get F10. F10 goes to F9. F10 again goes to F11. F11, this is useless. So only F9. So our model is complete. We will add our sources here. This is my VT, SC1 or ET, so some kind of source. What is here? This is a constant. SC11 minus mg. So this source is constant because mg is constant. That is the input, whatever input you have. So pretty complex block diagram, but we have derived it. Drawn. So is this clear how this block diagram is drawn?
So,
Yes.
so if we write k before the integral, then what should we write the initial condition for the integrator?
I don't know. I don't know. If you write k before the integral. Okay. For mass, it's okay. It's momentum. Alright?
Yes, sir.
Right. Okay. For that, it is fast integration, then multiply with k. Okay. Otherwise, that has no meaning. Okay. No physical
Yes, sir.
meaning. So by double clicking these integration blocks, you can give in Simulink. Right. You double click on any of these gain blocks, it will ask you value. So you give value. Let's say JT is giving us. JT is, let's say, 1 kg for 2 kg per kg meter square. Then you double click there and put either 1 by 2 or straight write 0.5. It will take 1 by 2 also. If you write an expression, it will take. So you can write 0.5 or 1 by 2. You double click on this integration, it will ask you initial condition. So you give whatever initial condition you want. Alright? And if you want to change these plus minus signs in this sum blocks, you double click there. Once you double click this thing, there will be a box like this, where you have to put what you want to put. Okay. So you can put plus, minus, plus. Okay. If you do this, this is sum block data. If you put this, it will come as plus, minus, plus. This will give like this. Suppose you don't want this. Suppose you want this to be plus, minus, plus like this. Suppose you want it to be like this. And this is our out. Suppose you want. Then what do? You enter there. The first one is top one. Okay, so you don't want that. You put a 5. Then plus, minus, plus. This is the 5. 5. To give blank. 5 you will get. It's where is it in my keyboard? This laptop keyboard. It's there with backslash. Okay. Above shift backslash, it's giving 5. So you will put a 5 there and then you can rotate that one. You can add, remove all those things. So one thing that we recognize here is this transformer and gyrator. Transformer and gyrator, they always appear in pairs. GF and GY moduli appear twice in the model. That is number 1. Number 2, in any loop gain, GF and GY moduli are usually square. Usually square. Not any, some, at least one loop then. If you look at this, here is a loop. Look at this. Like this. So I will draw it like this. Then loop. And this one, this is a loop. So there are loops. And if you multiply all gains in this loop, right, then you will see this R element is appearing twice in the loop. Right. This loop gain. How much? This loop integration is, I will put 1 by S. ZD, 1 by ZD, R, so R square appears, ZD appears, sorry, ZD will denominator. ZD will denominator appears, ZD appears, and S square. How that happened? This integration is 1 by S. This is again another 1 by S. Okay, so twice integrated in that loop. So 1 by S multiplied by 1 by ZD, 1 by ZDS, R by ZDS into K into 1 by S. So R by RK by ZDS square, again multiply with R square. Likewise here, what is loop get? This is mu m by R. So 1 by ZDS, mu m square, mu m square R by ZDS square, ZDS. Okay? So in some loops, you will get square. In some loops, you will not get it. So in tomorrow's class, we will do some block diagram simulations. Right now, I will leave all this block diagram part, and I will go to something similar called a signal program. So I will move to something called a signal program, which is similar to block diagram. Okay? I cannot listen.